This is a fairly high-level introduction to Spark. Not a huge amount of detail. There will be a little bit of code, just to tease you. The idea is to talk about what Spark is, where it came from. So the first half is a little bit of history, just to give you an idea of the problem it's trying to solve. Again, trying to go back to the business problem. How it works, how you use it. And in the last step, just a little bit about the future of Spark, where we're moving towards streaming and how it fits into the streaming ecosystem, the new streaming world, which I'll mention later. So when we talk about Spark, we're talking about big data, so it's useful to have a definition. This comes from Wikipedia, and it's a bit verbose. Maybe a shorter definition is data sets that are too large to fit in the memory of a single machine. So if we have a collection, it's so big we cannot materialize it within the memory of a single machine. And so we need a way of processing that data over multiple machines and getting an answer and coordinating that work. And that's where Spark comes in. Oh look, I've got it there. So the story of Spark begins with MapReduce, which Ben mentioned earlier on. If you're not familiar with MapReduce, here we have an example of it in action. Obvious, dead easy. So the idea is we've got this collection that's too big to fit on a single machine, and we want to do a map operationally. We want to transform each element in that collection in some way to get another element, and then we want to combine all those elements together to get an answer. So we split the collection over multiple mapping operations on multiple machines. We reduce the responses we get from those mapping operations, and we create our answer. So that's it in a nutshell. Here's an example, and by weird coincidence, I've used a very similar phrase that Ben used. I don't know if that's some kind of synchronicity thing. So here's MapReduce being used to count the words in a sentence. So each map operation, each machine gets given a chunk of the phrase, and it generates key value pairs, and that's the important part. It's creating a key value pair. That's the answer. That's its product. And then those key value pairs are being reduced down, and we're adding up the instances of words. So that's, again, just a kind of foundation layer for MapReduce. But the real key to it was that it offloaded the difficulty of distributing a program from the programmer to the library designer. And there are other methods or other ways of distributing your application. Akka is a great example of one. But with Akka, you need to manage the configuration, the coordination of your program. With Spark, you don't, because it's solving a different problem. Akka is giving you a general purpose solution to a problem that can apply to a whole range of problems. Spark is about analyzing data, and this data analysis, we don't want to worry about the configuration. We want Spark to do that for us. So we want to express ourselves with a simple API. And this multi-tenant part is really about having the ability to run. The word is heterogeneous, but it's like we want to run data jobs that are completely different and bear no relation to each other on the same machines. So we want to be able to run. We don't want to have to set up a specific cluster for doing this analysis and then another cluster for doing that analysis. We want one cluster that we can shove any job we want onto and get an answer back from. And this is another slide that should really build, so ignore that bit for now. In a traditional data processing, I suppose traditional, because MapReduce is kind of traditional now, but we're going to have some kind of program, some kind of application, and it's going to contact the database and download a huge wedge of data and then operate on it and produce a result. So now we're into all sorts of problems because we can't fit everything onto the same machine anyway. But also we've got network problems, we've got fault tolerance problems, we've got all sorts of problems by shifting the huge amount of data over the wire. So we're into latency issues of I/O and all sorts. The solution that Google came up with was to put the data where it wants to be to begin with, and then just send the calculation over the wire. So rather than every job having to send not just the description of the calculation we want to do, but the chunks of data that need to be operated upon, we just send the description of the calculation, the description of the operation, and the reference to the chunks of data. And now each machine can just reach into its file system, its distributed file system, collect the data and do what it needs to do. So the benefits are fault tolerance, because if a machine blows up, we've got the data duplicated already. And more importantly, we've got the data distribution is occurring early on when it's saved. So it might be that that data is produced days or weeks ago, and we can perform many, many operations on it, and we don't need to move that data again once it's been distributed, saving on the I/O. Yeah, so where Spark comes in now, so that's MapReduce. But it's important to understand this kind of history. So we mentioned Mesosphere, DCOS. Where Mesos came into the scene, would it be 2010-ish? They did it, I don't know if is Ben still in the room? It's good. So this might be wildly inaccurate. I don't think it is. It was in 2010, the original Mesos paper included an example or a proof of concept for an execution framework that wasn't like Hadoop. It didn't load something from disk, do an operation, save it to disk. Load it from disk, do the next operation, save it to disk. It put everything in the memory because Mesos was all about sharing the system resources, and CPU and RAM were the initial shared resources. So the demo was, how can we share RAM? And how can we utilize that as a cache, load everything into memory, operate on it, and then move it off. And how much more quick is that than Hadoop? So the numbers here are from an official book, an official source, so I'm pretty sure they're right, but they give the right idea. They produced a logistical regression test in both Hadoop and in Spark. In Hadoop, we've got an average, roughly the same time every time it executes, 127 seconds. In Spark, the first iteration is longer, but then subsequent iterations are massively shorter. The initial first operation is because it's being loaded, it's being parsed and brought into memory, but then amortized over a long set of operations or a long number of iterations, we get a much lower overhead. So they proved a concept that it works, that it's useful, it has its place. But what is it? So Spark looks like this. You have a driver, which is you or I, who want to do our job, do our Spark job. We send our Spark job, we write our code, we package it, and we send it to the master via the CLI or however we want to do it. And the master manages the resource allocation, it breaks up that job, breaks up the chunks of the collection we want to operate on, and sends it to all our workers. And importantly, it's a service, it's not a library. So this is something that we set up the infrastructure and we send jobs to. It's not a library that you include in your application and it does some magic. And here's the stack. So Spark's great, it's really powerful. We'll see later on, it has some fantastically straightforward semantics and APIs, but that doesn't come for free. It's not just something you can just set up and run and be off to the races and do whatever you want and have all this magical power at your fingertips. There's a lot of infrastructure below and behind it, so it's just worth being aware that these are the types of things you need. So we've got the hardware layer, the actual machines these things need to run on, the jobs need to run on. We need storage, the distributed file system. We need a resource manager. It might be Yarn, it might be something else, but or Mesos fills both those gaps, really, essentially. Then we've got Spark, our execution framework for doing the jobs, but we also need a way of getting data in. Kafka's a good choice. We need somewhere to put the data to after it's been processed, And we need a way of visualizing it, otherwise there's no point in doing the job itself. So, as I say, it's worth bearing in mind this is not a straightforward, just run it on your laptop and off you go. You can have a local file system, but it's difficult to run in production. Now we get to the APIs. So how do you actually use Spark? So Spark experts may argue with this, it's been a bit oversimplified, but I think it's useful to have it in this kind of simplified state. Everything starts with the Resilient Distributed Data Set, the RDD. It's the atomic level of Spark. It's the lowest level thing you would touch in Spark. And it's essentially, the RDD is essentially a clone of the Scala Collections API. So pretty much everything you can do with Scala Collections, you can do with an RDD. And this means it's like a functional paradigm. So all of these map, filter, group by, distinct, whatever, these are functions that will take a function as an argument and execute that function, passing in each element of the collection. But where the Scala Collections API will work on a collection in memory, the RDDs work distributed across multiple machines and produce the magic that is Spark. But this is the very lowest level. Now this is a slide that should build, but essentially we're taking the same thing, the same word count, and just seeing what it looks like in Java at the lowest level API. So even though it might look a little bit verbose, this is the lowest level you're going to work at. So it's not too bad, really, considering how powerful this can be, because that's just one sentence, but this could be petabytes of data, of text data being counted. And it makes no difference. Your code wouldn't look any different. So we read in, this Spark object is a Spark session. It's just how we connect to Spark. It reads the text file, creates the RDD, splits everything by space. So from flat map, we get a stream of words, and then pairs them. Word number 1, and that gives us all the words with a count of 1 next to them. And now we reduce by key, and that's it. So it's pretty powerful. Well, I think so anyway. So above RDDs, we have data frames and data sets. Data frames are an attempt to take this RDD, the data over semi-structured data, something you can apply some kind of schema to, and build a table out of it. So named columns. And then data sets just move that a step forward by making it type safe. So here's an example. We've got our ages, our very accurate ages, I might add. And then we create a data set of people, strongly typed, and now we find the teenagers by just operating on the age column, and then take the names. So again, it's a fairly straightforward set of semantics for querying the data frame, creating a table, and then querying it. An even more easy way of querying a table is to use SQL. Lots of people are familiar with SQL who maybe aren't familiar with writing Java or Scala or any programming language, but a lot of people in data know how to write SQL. So Spark leverages that, providing a way of executing SQL queries on massive scales. And again, here's our teenagers. It's just SQL. There's no magic to what you need to write. And you can get results from, as I say, gigantic data sets. So just to flick back. And the APIs are polyglot. There's various different languages you can work with. I'm not sure how mature R is, but nobody uses R anyway, do they? So it's fine. And lastly, we come to Spark Streaming. And it's not streaming per se. It's not really streaming. It is. No, it isn't. It's micro-batching, I think is the term. Basically, it opens a window, And you can define the size of the window based on the rate of data that you're receiving. So it could be 0.1 seconds, it could be half a second, it could be a second, it depends. You can tune it depending on the frequency of data so that you're not opening and closing lots of empty windows. But you'll open a window, receive data during that time, close that window, and then operate your operations on that batch. It's kind of like an open-ended table. So it is a table, it uses data frames, but we're constantly appending to the table. And if you think about it, the true stream is just an open-ended table anyway, so it's a nice way of looking at it. And this brings us to one of the trends that we're seeing at Lightbend, a really big trend that we see at Lightbend, in the industry generally, but also specifically from our customers, where we're seeing big data operations, batches of data being reconciled at midnight in an hour, a job that takes an hour or so. And we're seeing that move to more continuous processing of data, so that companies are getting much more closer to real-time information for analytics, for prediction, and such like. So this is a really important field that Spark's trying to take advantage of, and doing a really good job of moving towards a truly streaming model. But the batch, the micro batch is really good, but they've seen the writing on the wall, they've seen this trend too, and they're making huge efforts to move towards it. So where does Spark fit into all the other truly streaming engines? So in terms of, we've got our product, Lightbend's product, Akka Streams there. Again, it's free, it's open source, you can download it and use it. And you can get sub-millisecond latencies. In fact, we just recently got sub-millisecond latencies from a proof of concept for a customer. But Akka Streams doesn't scale. It will run within one JVM and go insanely fast, but only on that JVM. You're not going to scale out with it. It's Kafka Streams there, which is fantastic. You load from one Kafka topic, you do some ETL load. How many X have I seen in the last minute? What's the last value of X I've seen? That type of thing. And then put it back on another Kafka stream. And then we've got Apache Flink, which is kind of a new kid on the block. I don't know if you know, but Google open sourced their data flow API, but they didn't open source all of it, just the top bit. The bit allows you to define the graph processing stages, but they didn't open source the runner. And Apache Flink is an open source runner for these Beam jobs, these Google data flow jobs essentially. Very low latency and scalable. So it kind of fits in, it beats Spark, but it's complicated. The semantics aren't straightforward. It's not easy to work with like Spark is, and it certainly doesn't have a SQL API to work with. So Spark fits in a little bit further up in that you're not dealing with super low latency, but not only are you getting pretty low latency, you've also got all the batch processing ability of Spark as well, because even companies that are moving to truly streaming models, they've still got other stuff to do. They've still got legacy work to do, and batch processing still has its place. Why go to all the effort of getting everything super real time if it's just not necessary? You've got to fit the business problem. And finally, machine learning is a really, really, really important part of the Spark ecosystem. Built on top of RDDs, but there's a newer, this has been deprecated, there's a newest version of machine learning, MLib, built on top of data frames. And vastly simplifies large-scale machine learning. Again, operating these kind of common operations, classification, regression, statistics, linear algebra, but again, on the petabyte scale if you need to. It's gigantic amounts of data. And what's really cool is you can import and export models. So we can share models, we can save things, we can try different versions, and we see that a lot with our customers. Training their models on data, using Akka Streams, for instance, to apply the new learning from new incoming data to existing data. So user information comes in, a model is retrained and then reapplied to existing user data. It's a very common use case, and Spark is just always there. Whenever anybody talks about machine learning at scale, the Spark is what they're using. Oh, that's it.